The next thing that we have to discuss is the Leslie matrix model. This is the second model that we have to discuss after the Lotka-Volterra model. So in the applied mathematics, the Leslie matrix is a discrete age-structured model of population growth that is very popular in the population ecology. So what is the meaning of this line? Now look, the data can be of two types. One type of data is called discrete. Another type of data is called continuous. Now what is the difference between discrete and continuous data set? The discrete data set is that data set which is generally don't have any kind of decimal value. If you have to define the number in the discrete data set, this can be full. For example, if I say you, what are the number of students present in this particular class? The number of students can be a whole number. This can be 5, this can be 10, this can be 15, this can be 20. This cannot be 15.5, this cannot be 10.2. It is not possible in the case of discrete numbers. But in the continuous data set or continuous numbers, the data can be present in decimal value as well. For example, if I say you, what is the average height of the students which are present in these class? So the average number of height or the average height of all the students can be a discrete number, can be a continuous number, can be a decimal number. The main thing is here. The height can be 5 feet 9 inch. It can be 5 feet 7 inch, or it can be also denoted in the meter value as well. For example, 1.2 meter, 1.5 meter, or whatever the situation. So here the possibility is there to be present in the decimal value. So that is the continuous data set. Again, example, if I say you, what is the average weight of the students which are present in the class? So again, that can be continuous. So this is the main difference between the discrete and continuous. So in the Leslie matrix model, because we are defining the population, the population cannot be in the continuous number, cannot be in the decimal. So in the Leslie matrix model, what we will do? We will define the age groups. For example, 0 to 10. Then we can say suppose 11 to 20. Then we can say suppose 30 to 30 to 40, not 30. Just look at this particular slide. This is 0 to 1 age. 0 to 1 age, how many individuals are there? One individual. In 1 to 2 age, there are two individuals. In 2 to 3 years of age, there are three individuals. In 3 to 4 years of age, there are four individuals. It is not possible that between 2 to 3, there are 3.5 individuals. It is not possible that in between 3 to 4, there are 4.2 individuals, because the individuals would be always in the whole number. So this thing is written here. The Leslie matrix is a discrete. It means it will be also, this will always have a whole number. It is age structured because we define the different age classes here, 0 to 1, 1 to 2, 2 to 3. So this is age structured model of population growth that is very popular in the population ecology. This is the meaning of this particular line. The Leslie matrix, this is also called as the Leslie model as well, is one of the most well-known ways to describe the growth of populations and their projected age distribution. So what you will do? You will create the different classes of age groups, and in these age groups, how many individuals or the number of the organisms you can count, you will count them and you will put them on that particular category. So this is what we do in the Leslie matrix model, in which population is close to migration, growing in an unlimited environment, and where only one sex, usually the female, is considered, because female are participating in the reproduction, you can say, because they are only producing the progeny. So that's why here only female are considered. So here the thing is that these are the assumptions, you can say, of the Leslie matrix model. No organism can migrate from that particular environment, and the environment is providing unlimited amount of food, shelter, everything. And we are considering only the 1:6 ratio, that is the female here. And the Leslie matrix is used in ecology to model the changes in a population of organism over a period of time. How it is changing over a period of time, that we can define with the help of Leslie matrix model. Then in the Leslie model, the population is divided into multiple groups based on the age classes that we have already seen in the next slide. And at each time step, the population is represented by a vector with an element for each age class, where each element indicates the number of individuals currently on that particular class. Like we have seen here in this particular slide. This is defining the number of individuals present in this age class. This number is defining the number of individuals present in this age class. Similarly, this one is defining the number of individuals in 2 to 3 years class. So similarly, we have multiple age classes, that is the I number, and we have multiple age groups, says X number. So here you can see in the Leslie matrix model, the population change can be defined as NT plus 1. It means what would be the change in population number in time t plus 1. One can be 1 year, one can be 1 hour, one can be 1 minute. So depending on the reproducibility of the animals there, organisms there, the NT plus 1 t can be defined. Here this is multiplied by the lambda multiplied by NT. NT is the number of individuals were present in the T time. And now we are calculating the number of individuals present in T plus 1 time. So where N is the number of individuals present in the population, T is the time interval of the interest. This equation says that the size of population at time T plus 1 is equal to the size of population at time T multiplied by a constant lambda. So when the lambda value would be 1, it means the number of individuals present in T time is equals to number of individuals present in T plus 1 time. So if the lambda equals to 1, it means that the population will remain constant in size over time. There would be no growth, as well as there would be no exploitation of these individuals. The number would be always remain constant, because NT plus is equals to plus 1 is equals to NT. If lambda is equals to less than 1, now the situation would be threatening for this particular organism. The population declines geometrically. It means within the time period, the population is diminishing, or it is declining. And when the lambda is equals to greater than 1, the population increases geometrically. So the lambda value or the positive value is good indicator in the Leslie matrix model. It means there would be good growth of the population in the upcoming time. The time would be T plus 1. This is all about the Leslie matrix model. One thing I would like to clear about, I want to make clear about that the no numerical questions generally asked from the Leslie matrix model as well as from the Lotka-Volterra model. Only the assumptions are important here, and the concept of these models are important here, and the formula you can see for the sake of the any kind of chance suppose formula is asked, so only that would be enough from the Leslie matrix model and Lotka-Volterra. Till now there were no questions you can find out from the Leslie matrix as well as Lotka-Volterra model. The next thing that we have to discuss is the survivorship curve. Now, what is the survivorship curve? So, survivorship curve is what you can see in your screen right now. The survivorship curve generally have percentage of organisms surviving in the y-axis and the time period in x-axis. And then you can see there are three types of curve can be found or constructed in the survivorship curve. Now, what the survivorship curve is defining? So, survivorship curve is defining the number of individuals present in any particular time. Here you can see the number of or percentage of organisms which are surviving. You can see here in the survivorship curve. So, here you can see this is the time and this is the percentage of the organisms. So, in this particular section here, you can see the type 1, type 2, and type 3. Three types of different survivorship curves you can find out here. In this particular survivorship curve, in this particular graph, it will tell you what type of organisms are there and what kind of the survivorship curve they are making. So here you can see the type 1 is making concave type of survivorship curve. Type 1 organisms are known as the concave shape survivorship curve organisms. Then we have diagonal organisms, which are type 2. Here you can see. And we have the third type, which is convex type of survivorship curve is created with the help of type 3 animals. So here examples are also included here. And here you can see the number of survivors in log scale is provided here in this particular scale. And in this scale, age in relative units or time you can say is provided here in this x-axis. So if if you look at the human beings, for the example, if you take the human beings, so at the very beginning or zero time, in this zero time you can see few number of the individuals are produced here, and these are constantly surviving up to the age, some age. And after that, completing that age period, which is like 60 year or 70 year for the human beings, they start dying and the survivorship curves immediately go down. In the case of diagonal shift or this diagonal relationship type 2, here you can see few numbers are born here in this particular zero time, and after that there is a continuous constant decline in the number of population or the survivorship on the organisms. And the example of these type of diagonal type of survivorship curve is found on the birds. Then we have the R strategist. Remember, R strategist organisms which are producing very huge number of progeny, and the survivalship of these progenies are very less. So here you can see at the starting, at the birth, there is a huge number of population present at the beginning. And with the time, there is a continuous decrease in the number of individuals till a particular age. And after that, the decline would be very slow. Especially that you can see in the larger trees as well as the organisms like frogs, snakes, and other reptiles, and all the marine vertebrates as well. So they will create the convex type of survivorship curve here. So survivorship curve is a graph showing the number of proportion of the individuals surviving to each age for a given species or group, for example, males or females. Survivorship curves can be constructed for a given cohort, a group of individuals of roughly the same age. So because the number of individuals which are present in this range, so these are having the same age group. So that is what it is saying in the last line. This is what survivorship curve is. I have told you there are three types of curves: type 1, type 2, type 3. Type 1 is called as the convex curve, type 2 is called as the diagonal curve, type 3 is called as the concave curve. So type 1, the convex curves are characterized by the high age-specific survival probability in early and middle life, followed by a rapid decline in the survival in the later life. They are typically of species that produce very few offspring, the K strategist, but care for them well, including humans and many other large mammals. So here the type 1, again in the graph you can see this is the type 1 human, and type 1 humans are convex curves. I think I have mispronounced earlier. So here this is the convex type and this one is the concave type. So remember it. Why you have to see in the lines from this particular side, then everything would be clear. If you look at from this particular side, you can see that type 1 is convex curve here. So type 1 is this is the convex curve here, and this one is the concave. While you are looking from this side, concave means the upfront portion in this particular same side, and here the downward portion, because this is bent in this direction, so this would be convex side. Then we have the type 2 or diagonal curves. These are the intermediate between type 1 and type 3, where roughly constant mortality rate, survivalship probability is experienced regardless of age. Some birds and some lizards follow this particular type 2 or diagonal pattern because there is continuous decrease in the population in the constant rate, with the constant rate throughout the population. Then type 3 or concave curves, these are the have the greatest mortality, lowest age specific survival we can say. For those surviving this bottleneck, this includes most marine invertebrates, as I have told you, and all the small organisms which are under the R strategist generally follow that type of concave curve in the survivorship curve, like this one, the lower one. So this is all about the survivorship curve. The next thing in the population ecology that we have to study is the population ecology itself. Population ecology is the study of the processes that affect the distribution and abundance of animals and the plant populations. So how you can see the change in the plant population or maybe human population, maybe any organism population. So how you can see the change in the population in a given time? So to see that, there is a formula that you can see here. This will tell you the change in population number in a particular time period. So here this is NT is the number of the population change in T time. This is change in population. N naught is initial number of population, which is in the T time, not T time period, which is initially staying on that particular environment or which are present on that particular environment. B is the birth rate. Birth rate are generally defined in the terms of per thousand. Suppose if I say birth rate is 5, what is the meaning of 5? It means per thousand population, the fives are or the five number are the increased number of population by the introduction or by the birth of the new individuals. Similarly, if I say death rate is 50, so it means the 50 are dying out of 1,000 every year. That is how birth rate and death rate are calculated. So B is the birth rate here per 1,000 per year. I is the immigration. Immigration means what number of individuals are coming from the outside environment. That would be the immigration. D is the death rate that we have already discussed. This would be subtracted. Birth rate, and the immigration are addition here are plus here by the new number of population by the older number of population, and death rate and the emigration which left the environment and go away to a new place. So these are subtracted from the initial number of population, and this is how you can see the change in the number of population in T time period. That is how population change can be calculated with the help of this particular formula. So very basic formula of the population ecology you can see. Then coming to the next thing, that is the growth models. Now in the population ecology, growth models are very popular to see the change in the number of individuals or change in the population with a given time period. The growth models are generally of two types, mainly of two types in the population ecology. So one by one, we will see the both models in very detail, including the numerical formula as well. So the very first type of growth model is here is the exponential growth model or exponential growth pattern, that is also called as J curve. Why it is called as the J curve? Because if you want to create a graph of this particular growth pattern, so there is a generally J type of curve is formed here. So that's why the exponential growth pattern is also called as J curve. Exponential population growth will occur in an ideal environment where resources are unlimited. There is no limited availability of resources, you can say. In such an environment, there will be no competition to place limits on a geometric rate of growth. It means in the given time period, there would be no competition between the organisms. Only then the growth would be exponential. A growth would be very high. So this is called as exponential growth rate. So in the initial, the population growth will be slow. Here you can see in this particular place, the initial growth of the population would be very slow, because in that particular time the shortage of the reproducing individuals is widely dispersed. It means the number of the individuals which can reproduce are less. That's why the initial growth is very less. As population numbers increases, suppose this reaches to this particular point, so after reaching to this particular point, the rate of growth similarly increases, resulting in an exponential or J-shaped curve that you can see here. And this maximal growth rate for a given population is known as its biotic potential. So let's see this in the graph itself. Here you can see the initial growth rate is very, very slow up to this point. Why? Because the number of individuals which were reproducing very less. And when the number of the individuals that can go up to this particular point, now the growth would be exponential in this space and the growth would be very high. So this is called as the exponential growth pattern or J curve pattern. So This maximal growth rate for a given population is known as its biotic potential. It means this is the limit of the growth rate. The growth rate cannot be more than this particular number. That is what this particular thing is saying. Exponential growth can be seen in populations that are very small or in regions that are newly colonized by a species. So, especially this can be found in the R strategist population, where the growth rate is very, very high, or the number of individuals which are reproduced are very, very high. If you look at the numerical formula of this exponential growth pattern, you can see here dn by dt is equals to Rn. R is the biotic potential or growth rate, which would be in percentage, which is also called as intrinsic rate of the natural increase or growth rate. So how to calculate it? Just you have to subtract these two, birth rate minus the death rate, and birth rate should be always higher. It should be greater than d, then only there would be growth takes place. If death rate is higher than the birth rate, then there would be no growth. So that is how this is defined. So dn by dt is the change in number of individuals, n is the number of individuals, T is the time period. So in T time, how the number of individuals are changing is equals to Rn. R is the growth rate here and the percentage value you can say. And this is multiplied by the N. N is the initial number of individuals before the T time you can say. So this is one thing. Now, if you again more explain this particular formula, you will reach to this particular point. This is NT is equals to by the differentiation or the mathematical people what they do. Don't go with that particular all thing. The main thing that you need would be this formula. That's all you have to remember. That is NT is equals to N naught e to the power RT. E is the exponential here. So the exponential value is fixed in the mathematics. So E value would be not provided you to the question. And T is the number of individuals in the T time, and not I have already told you the number of individuals in the zero time or before T time you can see. R is the growth rate in the percentage, T is the time period. If you have the value of N naught, R and T, so within that particular time period at this particular growth rate, what would be the new population you can calculate with the help of this particular formula. So you have to remember this formula, very important formula in the exponential growth pattern. Another type of questions that you can see from this exponential growth pattern in the Catalyst book or in the past papers is that if suppose there are group of number of individuals of amoeba or the microorganisms are present there and they are multiplying themselves in few time. Suppose they are multiplying in every 30 minutes. So initially in the zero time, there are one amoeba. There is one amoeba. After 30 minutes, there will be two amoeba. After 1 hour, 30 minutes more, there will be total four amoeba because now two amoeba will reproduce. And after 1.5 hours, there would be eight amoebas. So this kind of exponential growth would be continue. So how to calculate new number of individuals if population is doubling after each time, so that you can calculate with the help of this formula. New population nt is equals to n naught, the initial population, multiplied by 2 to the power n. Why 2 to the power n? Because they are multiplying themselves in n time, not n time, in t time we can say. So how to calculate the n here? N is a kind of factor here, or you can say multiplication factor here. If I say multiplication factor, so how to calculate this multiplication factor? That is very simple. Suppose if I say the amoebas or the microorganisms are doubling in each 5 minutes, and what would be the new population in next 1 hour? So how to calculate n? N you can calculate by dividing these two numbers, larger number divided by the smaller number. So larger number here is the 1 hour, so that would be the 60 minutes divided by 5 minutes. So the n is equals to here would be 12. So you have to place 12 here in the place of n. So n is a multiplication factor that you can get by dividing the larger amount of time divided by the smaller amount of time. So that is how n can be calculated. And this formula you have to use only on that situation when population is multiplying itself in the t time. So the population is just doubling itself in the t time. So only on that situation you have to use this formula. In remaining all situation, if growth rate is provided, time is also provided, then you have to use only this formula. This formula is generally not used, or no questions are generally asked from this formula. The two main formulas are these. Then in some questions, the T is asked, time period is asked. So whatever time period is provided or asked in the examination, what you have to do, you have to remember the rule of 70 only. What is the meaning of the rule of 70? It means suppose you want to see in how much time population is doubling. This is population, and population in T time is now 2 multiplied by population. It means population is doubled now. And how much time is required to such situation? For example, suppose growth rate or R is provided 15%. So what do you have to do? You have to just use the rule of 70. So T is equals to 70. 70 divided by 15. This would be 4 point something. 4.66 or 67 you can say. So the rule of 70 only works on that situation when population is doubling, population is having the 2x value, the new population value is 2x now. So only on these situation you have to imply the rule of 70. The rule of 70 is not true for any other situation except for this one. So do not imply rule of 70 if population is not doubling. Suppose it is saying the initial population is 1 billion, and after the T time, the new population is 1.5 billion. So don't use the 70 rule. You have to use this particular formula there. The 70 rule would be only true on that situation when population is doubled from the initial value. So that is how these formulas you can apply. The first formula is the general formula. Second formula for the amoeba type of questions when population is doubling in the T time and the new population is asked here, population number is asked here. And suppose in the same doubling situation, if it is asking the T, the time period value, then you can use the rule of 70. 70 divided by R in percentage you have to just put, and you will get the time requirement for just doubling the population. So this is all about the exponential growth pattern or J curve population ecology. So I hope this is clear to you. This will be more clear when we will complete the numerical questions, which are already enlisted in the upcoming slides. So don't worry that then this thing would be more clear to you as well.